I came across this old but beautiful hard drive and was wondering, is it still working? Is the data accessible somehow? Can I bring it back to life? The type label says it is an NEC D5146H drive, obviously from July 1988. Funny thing that the manufacturing date is handwritten, and also this table of erroneous bytes, which faded already a little and is hard to read. But I presume this has been taken into account during low-level formatting, so that's most likely nothing to worry about. I'm also curious about how heavy it may be, because it feels quite massive. Okay, about 1.6 kilos. A little research quickly revealed some more facts. It's an MFM drive with a spin rate of 3600 RPM, 8 heads, 4 platters, and a total capacity of 42 megabytes, which was quite top-notch at that time. Okay, first test. Just power the thing up and see if it spins up nicely. This locking mechanism of the stepper motor retracts. Yeah, what a sound. And the stepper motor for head positioning is moving, so it does some calibration, that's good. So it's worth to go on. At this point, normal people would look for a suitable MFM controller, and maybe such a thing would be still available, at least with a nicer bus interface. Then you would only need an old PC where you can plug that thing in. And done. Easy, huh? Nah, where would be the fun and the challenge? That's all I have so far. The drive itself and one of the two cables. The other one is missing. Let's worry about that later. Let's investigate that MFM interface. It has two connectors, a 34-pin control connector and a 20-pin data connector. Let's start with the easy part, the control connector. I made this small adapter board for the 34-pin plug, which is the same size and format as floppy drives have, so I cut it out from an old floppy drive. So we have easy access to the signals and can use it with a breadboard. There are only a few signals of interest. First, there are 4 drive select pins. Assuming this drive was the one and only hard drive in its computer, we just need to hardwire the drive select 0 pin to ground and leave the others open to permanently select drive 0. Next, there are 3 head select pins. We just leave them open to select head 0, which is fine for now. Let's check the other control signals live in action. When powering up, the index signal comes to life first. It gives a pulse for every rotation of the disks. After spinning up, the ready and receipt complete signals go active, and in this case also the track 0 signal, meaning that the heads are currently positioned on the outmost cylinder. Let's try to move it. Therefore we must set the direction in signal to low first, and then create some pulses on the step signal. Yes, the stepper is moving and the track 0 signal went inactive. We are no longer on cylinder 0. Okay, let's move back. Finally reached cylinder 0 again and the track 0 signal went low. A closer look at the index signal shows a nice frequency of 60 Hz, which means that the disks rotate at a constant speed of 3600 RPM as expected. Power down doesn't show any surprises. All the control signals went inactive quite simultaneously. Now it's time to focus on the data connector. Luckily I found a proper plug and could make a data cable from an old floppy cable. However, I've shrinked the footprint on the host side from 20 to 10 pins by leaving out the unused pins and some of the ground pins. Let's take a closer look at the MFM read signals with the oscilloscope. Yeah, there's the data. A differential transmission is used for the MFM signals. So the two MFM read signals show the same signal but with inverse polarity. In order to get the proper digital signal, we need the transceiver chip. I'm using an SP485E, which is a half-duplex RS485 transceiver. Half-duplex is totally fine, for we only need the receiver part of the chip. If we would ever consider to also write to the hard drive, we would need a full duplex transceiver with separated A and B lines for both directions. I've made this little breakout board for the transceiver. For the sampling of the raw MFM data, I'm going to use this little fellow here. It's a small logic analyzer. We've already used it before shortly to analyze the control signals, but now it's going to show its true power. And there is already a problem. The MFM pulses have a length of 50 nanoseconds, which is only a little longer than the sampling interval of the logic analyzer. Its sampling rate of 24 MHz means a sampling interval of 41.7 nanoseconds. So these pulses are always measured as either 41 or 83 nanoseconds, which isn't nice. And in some bad cases, we might be even missing one or another of the pulses. In order to make the sampling process more reliable, I'm going to add a D flip-flop. A D flip-flop like this 7474 can be used as a frequency divider by connecting its inverting output to the data input and feeding the input signal to the clock pin. Then the output of the flip-flop transitions with every rising edge of the input signal. You can say the frequency is divided by 2. In our case, we don't have a strictly periodical signal. Therefore, we get a waveform where every transition represents a 1 pulse of the original signal. That looks much better, and it looks like this signal can easily be sampled with our 24 MHz logic analyzer. But what do we have to expect anyways? How does MFM work? An MFM signal is a combined clock and data signal. Therefore, a real MFM controller uses a specialized data separator chip like this ADN 2814 chip. Quite complicated stuff with a so-called PLL or phase-locked loop for the regeneration of separated clock and data signals. We don't need this. Taking a closer look at the MFM specification, it turns out that there are only 3 different patterns possible. Between two 1 bits, there are either 1, 2 or 3 0 bits. That's all. So we only need to measure the intervals between the 1 pulses, more precisely the intervals between the transitions in our modified MFM signal. And in our 5 megabit data stream, these intervals can only be either 200, 300 or 400 nanoseconds. That shouldn't be too much of a challenge. Well, in fact, there is a problem again. Our logic analyzer has a natural sampling tolerance of plus minus 41 nanoseconds due to its sampling rate of 24 MHz. Let's additionally assume that the original signal also may have a tolerance of plus minus 20 nanoseconds. Then we get a total tolerance of plus minus 61 nanoseconds. So our 200 nanoseconds may be measured as 139 to 261 nanoseconds, 300 as 239 to 361, and 400 as 339 to 461 nanoseconds. We see the ranges are overlapping. Measured values of 240 to 260 nanoseconds as well as 340 to 360 nanoseconds cannot be clearly assigned to one of the expected MFM patterns and therefore have to be considered as erroneous measurements. I've already programmed an MFM parsing routine. It takes the raw data from the logic analyzer and first separates the data for every captured disk rotation triggered by the index signal. Then it calculates and quantizes the intervals by using our tolerance rules and translates them into the simple interval symbols 2, 3, 4 or the letter E for erroneous measurements as a kind of intermediate syntax. The result of our track 0 looks like this. a sequence of the 3 interval types with errors here and there. Too many errors for a proper decoding. Luckily, we are not bound to the sample data of just one disk rotation. We can sample as many as we like. There are 60 of them every second. If we look at the data of 3 disk rotations, we see that the data match quite well and there are errors in every sample set, but at different locations. So the next thing our MFM parser has to do is to merge the data of multiple disk rotations and eliminate the errors as good as it gets. This was a bit tricky to program, but now after about 6 to 10 iterations we get a quite clean data stream. Surprisingly, there are still errors in it, but these errors seem to be real errors in the magnetic data, which might have occurred at the start and stop of every write access. But now the data should be good enough for the real decoding. The principle of decoding is this. As mentioned earlier, the MFM stream is a combined clock and data signal. Therefore, we always need to know if the last detected 1 pulse belonged to the clock or the data. In our case, it's the last detected edge, which belongs to one of 3 states: unknown, clock or data. Let's play through one decoding step for better understanding. Let's assume the last edge was a clock bit. When there is a next interval of 2, then we know this is also a clock bit and we have missed a 0 bit in between, which we have to add to our decoded data stream. The last edge state doesn't change. On an interval of 3, we have also missed a 0 bit in any case, and the current edge belongs to the data. Therefore, we add a 1 bit to the data stream and change the last edge state to data. Finally, an interval of 4 means that we have also missed a 0 bit, and the current edge is a clock bit again. Therefore, we have to add another 0 bit to the data and don't change the state. According to the MFM specification, an interval of 4 is only allowed for data bits. So in this example, we would have detected an MFM code violation, which is also important. We will come back to it a little later. Now the main problem is, if we jump randomly into the raw MFM data, we will never know if the 1 pulses belong to clock or data, and we also don't have any byte boundaries. In order to synchronize the decoding process, we need to know what data we have to expect. This is the track format taken from the Seagate ST412 manual, which we can take as a reference. After the index pulse, which marks the start of the track, there should be a pattern of 16 4E bytes followed by 13 0 bytes. That's what we have to search for. First, we need to know how these patterns look MFM encoded. We take the binary data of 4E, then we add the clock bits according to the MFM rules. By combining the 2 data streams, we get the MFM stream. At last, we translate it to our interval syntax, and here is the 4E pattern. 3, 3, 3, 2, 2, 3. The same thing for a 0 byte. This ends up as a consecutive series of the interval 2. Back to our MFM parser. Here is the 4E pattern again. We search for it and count the repetitions. Afterwards, there must be the 0 pattern, where we count the occurrences of consecutive 2 intervals. The pattern search is successful when there are more than 80 of them, which means that there are at least 10 0 bytes. Then the real decoding can start, as already shown. An important thing during decoding process is the correct detection of the field markers A1FE for the address fields and A1F8 or FB for the data fields. These A1 bytes are special because they violate the MFM encoding rules on purpose. A normal clock substitution for A1 would be 0E. But in this case, a sync clock of 0A is used, which results in a missing clock bit in the MFM stream. So these sync marks cannot be mixed up with normal A1 data bytes. Therefore, there is this MFM violation detection mentioned earlier, which we correlate with the occurrence of field markers. In this way, we always know if the current data belongs to an address or a data field. Finally, all decoded binary data chunks are stored away. Now let's see what we have captured so far. Remember, we have currently hard selected head 0 of cylinder 0, so we will only see track 0 for now. Okay, we've got 34 data chunks. Obviously, alternating address and data fields given by the alternating file sizes of 34 and 532 bytes. That's a little surprise because I expected 32 sectors per track with 256 bytes each, according to the Seagate specification. But this hard drive is obviously already formatted with 512 byte sectors. Let's look into the first data chunk. It starts with the 4E pattern, followed by the 13 0 bytes as expected. Very well. Then A1FE, the marker for an address field. Cylinder number 0, here is the head number 0 and the sector number 1. And finally a 16-bit CRC checksum. Here is the moment of truth. The next data chunk must be the corresponding data field with the first sector of the disk, which is the master boot record. And here it is. Again, it starts with a sync pattern of some 0 bytes, followed by A1F8, which is the data field marker. Then the real sector data, which we will look at in a moment, and finally a 32-bit CRC checksum. Okay, how should an MBR look like? The biggest part of the sector is the bootstrap code. Then the most important part, the partition table with up to 4 partition entries, and at last the boot signature 55AA, which is the marker for a bootable sector. Every partition entry has a status byte, which is either 80 for a bootable or 0 for a non-bootable partition. Next, there is the address of the first sector of the partition in cylinder head sector notation. Then 1 byte with a partition type. Let's look it up when we know what we have to deal with. Next field is the address of the last sector, also in CHS notation. And finally, the first sector is an absolute number and the total numbers of sectors in the partition. Let's compare it to our captured data. I've already stripped the plain sector from the data field chunk. It starts with the bootstrap code, where we can almost read some error messages in German. At the end there is the boot signature 55AA, and directly above there is the partition table with only 1 partition entry. Status byte 80 says this is a bootable partition. Next 3 bytes is the start sector. It's head 1, sector 1, cylinder 0. Then the partition type 06 means it is an MS-DOS partition with more than 32 megabytes. The following 3 bytes is the last sector. These decodes as head 7, sector 17 and cylinder 613. Then there is a 32-bit value of the absolute number of the start sector. It's 17. And finally, the total number of sectors in the partition. It's 83,487 sectors, which means a partition size of about 40 megabytes. The rest of track 0 only contains empty sectors, so it's time to go on. First, we need to control the head positioning. For this purpose, I added an Arduino Nano board to the hardware setup I've already shown. This is the complete setup we need. The connector for the data bus with the RS485 transceiver and the D flip-flop, which prepares the MFM data for our little logic analyzer. Then the control bus, which is now mostly connected to the Arduino board, except for the index signal, which goes also to the logic analyzer. The Arduino board is controlled via serial interface from my MFM Explorer program, which meanwhile has evolved into a Windows Forms application. Here we set up the connection. Below there is a little terminal window that shows debug and output messages from our controller. On the right, we can visually observe the status lines of the hard drive. Let's power the drive up again and see what happens here. After spinning up, all the status lines go active. So the drive is ready, seek is complete, and we are still on track 0. Now we can set the cylinder and head positioning at any track we like. And we can read the addressed track with the logic analyzer. What I haven't shown so far is this remote control of the logic analyzer. The corresponding software is called Logic 2 by a company named Salier. I hope my pronunciation is somewhat correct. This program has a real simple automation interface. Therefore, this Logic 2 automation package must be installed, and then the automation server must be either enabled in the settings of the program, or it gets directly started from my MFM Explore program with the correct command line parameters. Then we can control the logic analyzer with a little Python script, which I've based on the given example of Salier and simplified it even more. I'm choosing a capture duration of 0.2 seconds, which is sufficient to capture about 12 rotations of the disk. Remember, we need multiple sample sets of the same track to get an error-free data stream. This way, all the threads come together in my MFM Explore program, and we can read any track we like. So let's capture track number 1, which contains the boot sector of our partition. And here are the 17 sectors of cylinder 0, head 1, where sector 1 is the boot sector. Wow, it's already an MS-DOS 5.0 installation. Honestly, I've expected an older one. We can also read the volume name, its support PC, and that it is a FAT16 file system. Towards the end of the sector, we can read an error message in German again, and also the names of the first system files to load, io.sys and ms-dos.sys. 55AA at the end is the marker for a bootable sector, which we have already seen in the master boot record. My MFM Explore program retrieves some more data from the boot sector. We already know the sector size of 512 bytes and an official confirmation that we have 17 sectors per track. The media descriptor F8 just says it's a hard drive. What a surprise! Then more information about the file system, like the number and size of the file allocation tables, the number of sectors per cluster, which is the minimum file size, the number of root directory entries, and the total number of sectors in the partition, which is about the whole disk size of 40 megabytes. Before diving deeper into the file system, I would like to know about the quality of the captured data. Therefore, we have to verify the CRC checksums we get from each address and data field. But how to do this? I didn't even know which types of CRC are used here. Luckily, I came across this fine piece of software, CRC Revenge, which can not only calculate hundreds of different CRC algorithms, but can also find out the correct algorithm by providing some data examples with the corresponding CRC. With this tool, I could find out that for the address fields, a 16-bit CRC algorithm is used named IBM 3740, which absolutely makes sense. For the data fields, a 32-bit CRC is used, where no specific name could be given, but the parameters were revealed. With this information, I've added the CRC check to my MFM parser by integrating this CRC Revenge tool. And let me tell you this, I didn't encounter any CRC errors, not a single one. I'm happy to see that the captured and decoded data is 100% reliable. Now we can finally explore the file system. First we select the one and only partition we have. reading its boot sector again, and now reading the file allocation table and the root directory. Here it is, with the system files iosys and ms-dos-sys, and also the config-sys and autoexec bat files, which may wake ambivalent memories about the MS-DOS days back then. Let's take a quick look at the DOS directory first. Okay, that's how an MS-DOS installation looked like. Installation date was obviously October the 2nd in 1991. And what do we have here? A Norton directory. No way! This is the legendary Norton commander, the prime father of all file managers. Let's copy this Norton directory with our built-in xcopy function. Just select the destination directory and off we go. Okay, this may take a while. Every pop-up of a diagram in the Logic 2 program represents the reading of one track with 17 sectors of the MFM drive. Meanwhile, let's have another look at the complete hardware setup of this project. Here we have an old AT power supply with nearly the same age as the hard drive. And it has a real power switch. Of course, every other would have done as well. Then the MFM drive itself, the logic analyzer, and the breadboard with the Arduino Nano and the connector boards I've shown earlier. Unfortunately, there's not much more to see here. No blinking lights or special sounds. Maybe I should have added some LEDs to make the experience more exciting. Anyway, here's the schematic again. Of course, you can find the whole KiCad project as well as the MFM Explore program and the corresponding Arduino sketch on GitHub. All the related links are in the description below. I've even designed a PCB which would look like this. Isn't it nice? However, I haven't ordered it because first, this video is not sponsored by any PCB manufacturer. And second, it's just simple enough for the breadboard. Well, it's still not finished, so let's speed things up. Meanwhile, I've successfully extracted the whole data, which was about 24 megabytes, and it took 1.5 hours all in all. I think that's not so bad considering the circumstances. Unfortunately, the old 16-bit DOS programs are not executed natively on Windows anymore. Therefore, we need the DOS emulator like DOSBox. Now we can finally look what we have got here. As expected, the Norton commander. We can use it directly to browse through the content. And also its Starry Night screensaver is still here. Isn't it nice? What else have we got here? QBasic is a good start. There should be some games at least. Let's try out gorilla.bus. Okay, not bad. How about nibbles? That looks like fun. Let's tune it down a little so I can come to some kind of conclusion of this project. Okay, all in all, I found out that this hard drive has been used for about 2 years, from October 1991 to September 1993. I haven't found any files younger than that. And it was obviously used in a software company because I found some software specifications and also some fragments of source code by restoring the deleted clusters. Unfortunately, no hidden bitcoins or something spectacular. Anyway, this was a very nostalgic experience for me, and I learned a lot about MFM encoding, cyclic redundancy checks, and the history of hard drives in general. I hope you liked it as well. Thanks for watching and see you soon.